Hi everyone, this is part 2 in a series of videos on the topic of linear programming. In the last video we talked about the background behind linear programming, why it was invented, and where it is used today. And in this video we will look at two problems and just go through that process of solving a linear programming problem. Alright, so first of all, let's find the maximum and minimum values for an objective function subject to a series of constraints. Alright, so in this example, the objective function has already been written. We have z equals 6x plus 8y. Now we could substitute in, like, maybe this represents profit, or maybe this represents a cost. So that's why we're interested to find maximum or minimum values. Okay, so once you have, this is step 1 to write the objective. And then step 2, you write all of the constraints of the problem. Now step 3 is to graph these constraints. So that's going to be our next step. Alright, so remember, for graphing inequalities, we want to graph the boundary lines and then shade one side or the other. Right? So to graph lines, we could either choose points that are true, right, or we could use slope-intercept form. Alright, so for these, I'm going to choose to do points, just because these are x plus y. It seems like we could find some points fairly easily. And I think I'm also going to find the intercept, because I'd like to know, what scale to use for my axes. Alright, so if we substitute 0 for x, this is finding the y-intercept. Okay, then y needs to be 200. So remember, I'm pretending that there's an equal sign right there right now. And then if I make y a 0, then x must be 200. All right. The second equation, the intercepts, similarly are 0, 450, and 450, 0. Okay, and then x is less than or equal to 200. Well, the line x equals 200 is a vertical line through 200 on the x-axis. Okay, and then these constraints, these will typically show up in a problem because your variables will be things that can't be negative numbers. So if we're talking about like units of a product that's being made, or if we're talking about how many tickets are being sold, or something like that, these would need to be either positive or equal to 0. So essentially what those do, I don't usually graph those two lines and bother to draw them in, because they are actually the axes on your plane. So instead what we do, right, if you're looking at a coordinate plane and you're going to graph, if x and y need to be either positive or 0, then really what we're doing is we're only looking at graphs in this first quadrant. So instead of really drawing in those two lines, instead, when I go to make the graph, I might just choose to only draw the first quadrant, and then I'm just staying in this region. Alright, so let's make a graph of these inequalities. Alright, so the first one, x plus y is greater than or equal to 200. Alright, so I'm going to plot the intercepts. And here I've chosen a graph. Let's see, this one's going by 25s. Okay, so I plot those points and then connect with a line. Okay, and this keeps going, but that's good enough. And then we need to decide which side to shade. So if I plug in 0, 0 as a test point, get rid of this. Okay, so if you plug in 0, 0, you end up with 0 is greater than or equal to 200, which is false. So I want to shade the side that does not have 0, 0. Now I'm just going to draw a little arrow. I don't actually want to shade, since I'm going to have so many different constraints here. All right, but I do want to indicate that that's the side of the line to be shaded. Okay, the second one, x plus y is less than or equal to 450. All right, so I had this one. Okay, and then the intercepts are at 450 on each axis. And that's here. And here, and then connect those with a line. And that's a little bit off. Let me try that again. Okay. All right, that's decent. And then a test point, let's do 0, 0 again. And we end up with 0 is less than or equal to 450. That one's true. So we want to shade the side of the blue line which has 0, 0. Okay, so that's going to be below the blue line. All right, and then x is less than or equal to 200. We said that that's a vertical line through 200 on the x-axis. All right, so I'll put that one in. Let's see. Let's do a different color. How about red for that one? Okay. And a test point of 0. That's going to give 0 is less than or equal to 200. And that's true. Okay, so I need to stay to the right of the red line. Okay, and then the two constraints that x and y are greater than or equal to 0. That means that I need to stay in this first quadrant, so to the right of this axis and above this axis. Alright, so if you follow all of the arrows and see where we should be shading, well, it looks like I need to shade between the blue and green lines. Okay, but I need to stay to the right or to the left of this vertical red line. Alright, so it's actually this region in here is shaded. Alright, so you can choose to shade if you want, or just somehow think about or mark where that solution set would be. But that region represents all of the points that satisfy all 4 of these inequalities. Alright, so these are the points that do meet that constraint. Alright, that set of constraints. So now what I need to do is find the maximum and minimum values of this objective function. Alright, and I'm going to do this by testing the vertices. So what I wanted to do is to figure out what the coordinates of each vertex are, write those down, and then I'll have something to be able to substitute into that equation. Okay, so step 3 was graphing. Then step 4, find the coordinates. Alright, so I have this blue one. This was an intercept. I know what that is. Alright, that was 0, 450. Then I have this green one down here. That was another intercept from the green line. Oops. Okay, that was 0, 200. Same with this one down here. That's 200, 0. And then the other corner of the shaded part is this intersection of the red and blue lines. So the nice thing is that one of those lines is vertical. I know for sure that the x-coordinate is 200. So what I need to do then is just figure out if x is 200, I want to figure out what that is on that other blue line. Okay, figure out what the y value is. So the blue line was this one. Alright, so basically what I'm doing, I'm making a system of equations. X plus y equals 450, and the line x equals 200, and then I'm trying to figure out what y is. Alright, so you can probably see this from the graph if you've drawn this accurately, but if not, then use substitution. So substitute in 200 for x and solve for y, and that tells us that y is 250. Okay, so if you look back at the graph, let's make sure. Alright, and if you follow this over, yes, that does look like it's at about 250. Alright, so that seems fairly accurate. Okay, so those are the 4 vertices of the region. And then notice I do have other intersection points, like I have, this point down here and this one. Oops. Okay, and then I have like a red. Let's see, I've used the red one. This may be the only one that I didn't use. But we are only looking at vertices of the shaded feasible region. Alright, we're not looking at any of the other intersection points. Okay, so the last thing I need to do is just test these vertices in the objective function and see which one gives the maximum and minimum values. Alright, so I like to make a chart for this. Okay, and I do a column for the points, the coordinates of the vertex. And then the objective function is 6x plus 8y equals z, and then z is going to be like profit or cost. So then I just go through and list the points and plug them all into the equation. Alright, so here are the points, and okay, so the first one, substitute 0 for x, 450 for y, and then find the corresponding value of z. I'm running out of room, so I'll write this over on the left. Okay, so 8 times 450, that's 3,600. Okay, and then, okay, here we go, 200 for y, that gives 1,600. Then 6 times 200 plus 8 times 0, 1,200. And then 6 times 200 plus 8 times 250. And that one's 3,200. Okay, so then the maximum value, just choose the biggest one, so the maximum value is 3,600. And then the minimum value would be 1,200. Alright, let's try another problem. Often these are presented as word problems because they, in real life they would be word problems. And then the goal of a mathematician would be to formulate these problems and to write them in mathematical terms so that then a computer could then run the math and figure out and solve this problem. All right, but an operations research specialist is needed in order to phrase this mathematically. Okay, so here's the problem. Phil owns a small business that makes playground sets and playhouses. The production process breaks down into the prep stage, where lumber is cut and drilled, and the assembly stage. For each playground set, it takes a worker 2 hours to cut and drill the lumber, and another worker 1 hour to assemble the unit. For each playhouse, it's 1 hour for cutting and drilling, and an hour and a half for assembly. Workers never work more than an 8-hour day. Phil makes $100 profit on each playground set sold, $75 profit on each playhouse, and our task is to use linear programming to decide how much of each product the company should make each day in order to maximize the profit. Okay, so step 1 is to write an objective function. Now we need to know what the variables are in order to do that. So if you look at the last sentence here, decide how many of each product the company should make to maximize profit. Right, so those are the two variables, and if you back up to the beginning, the two products are playground sets, let's call that X, and playhouses, let's call that Y. Alright, so the objective is to maximize profits. You want to write an equation for profit. Okay, and there's always a sentence in here that will tell you what the profit for each of those things is. So you find that, and it's $100 for each playground set, so that's going to be 100 times X. And then we also have the component for profit from the playhouses, 75 times Y, the number of playhouses. So that's the objective function. Okay, now we can go through and we can just cross out that whole sentence. We've used that. Alright, now we're looking for constraints. That's step 2. So any restrictions or limitations on the number of sets of playgrounds and playhouses that can be produced. Alright, so notice we have this sentence that describes the workers. The workers never work more than an 8-hour day. So there's a restriction on time that we have to describe mathematically. Alright, so a worker's time has to be less than or equal to 8 hours. Alright, well, back up again. there's one worker doing the cutting and drilling, and there's another worker who is assembling. Okay, so we actually have two workers here, and their time each has to stay below 8 hours. All right, so if we look at the worker who's doing the cutting and drilling, well, he spends 2 hours on the playground, and he spends an hour cutting and drilling on the playhouses. Okay, so he spends 2 hours times every playground set plus an hour for every playhouse, and that describes the total number of hours that he works each day. All right, so notice, for example, he couldn't make like 10 playground sets and 10 playhouses, because then he'd be spending 20 hours on each of those things, and that's definitely over his 8-hour workday. Okay, second guy. Second worker spends 1 hour assembling on the playground sets, so that's 1x. And then for the playhouses, he spends an hour and a half assembling. And his time also has to stay below 8 hours. All right, and then finally for constraints, we have two that are always implied. So think about the minimum values for how many playground sets and playhouses can be produced, and you can't produce negative amounts of those things. So we always have x and y greater than or equal to 0, unless there's an even tighter restriction, like maybe we have to produce 100 each of these things. Right? But if it doesn't mention anything about a minimum amount, then assume that it's 0. All right, so we have 4 different constraints here. All right, and in step 3, we need to graph those constraints. All right, so I'll let you do this on your own, and I'm just going to create and then show you a finished graph of these constraints. All right, so here's a graph of the 4 constraints, and the intercepts for the 2 lines, one of them turned out to be 8 and 4, and then the other one turned out to be 8 on the x-axis and 5 1/3 on the y-axis. So I just did my best to estimate where that would be, drew that in, and connected the lines. All right, so if we looked at the shading, you end up shading below these 2 lines and then staying above and in that first quadrant for the x and y axes. All right, so the shaded region, this is going to be the feasible region that fits all of those requirements. All right, so vertices for the region, this is the weird 5 1/3 one. So what I want to do for substituting this into the function, I want to make sure that I don't round, that I actually leave that as 5 1/3. All right, so that's the point 0, 5 1/3, or you could say 16/3. Okay, and then I have the other one or the other 2 that are fairly clear. This one, this is the 0.40, and then over here we don't want to forget the 0.00. All right, so in cases where you're looking for a maximum, we know that that's not going to be the maximum value, but it may be the minimum value, and it's still important to test that in the function. Okay, and then I have this other point, which is the intersection of the 2 lines that I graphed, and because my graph isn't quite accurate, it's a little bit off. It seems to be the 0.24, but I would want to check this to make sure that that's accurate. So what I did is I just plugged that into the 2 equations, the 2 inequalities, and I made sure that when I substitute 2 and 4 for x and y, that I still get 8 in each of those equations. And I did, so that is the correct intersection point, or 2, 4. Okay. So now the last step is to test these vertex points in the objective function to see which one gives the maximum profit. All right, so I'll make a table for these. Okay, go through and substitute in these values for x and for y. and then see what values you get. Here are my values. So the largest one is 500. Right? Now, I would also like to throw in a sixth step here. Let's actually finish and answer the question. So if we look back at the problem, we were asked to find how many of each product the company should make each day in order to maximize the profit. So if you just wanted to interpret this, then we would just state what the values of X and Y are, what they represent. Okay, so I could say make 2, I think this was playground sets, 2 playground sets and 4 playhouses each day to maximize profits. And then if you're asked what the maximum profit is, the maximum profit is $500. Okay, and that's it. That's it for a linear programming problem. Alright, in the next video we will look at some of the steps and break this down, do some practice with writing the objective function and writing the constraints, and then we will go on and practice the rest of the parts of the problem. Alright, thank you for watching.